Hey guys, tonight we begin with buildings designed to kill you that somehow learned not to. Medieval castles, structures where every architectural decision was simultaneously about defense and survival, where the same stone walls that kept enemies out also trapped smoke inside, where height meant military advantage, but also architectural nightmare. Genius engineering that solved problems most people didn't know existed, all without causing mass panic when night fell and fires were lit throughout buildings designed to burn. If architectural problem solving disguised as fortress design sounds fascinating, take a moment to like the video and subscribe to Candle History. Drop a comment letting me know where you're watching from and what architectural features your building has that medieval engineers would have envied. Pour something warm, get comfortable, and let's explore how medieval builders created structures that managed wind, smoke, heat, and human survival through sheer cleverness and centuries of trial by fire. Medieval castles faced a problem modern buildings solved with HVA systems and building codes. You need fire for survival. Fire produces smoke. Smoke kills people. Your building is made of stone, which seems fireproof until you realize stone walls trap heat and smoke wonderfully. The spaces need to be defensible, which means small windows and thick walls, which means terrible ventilation. And you're housing hundreds of people who all need warmth, cooking fires, torches for light, and somehow breathable air. The early solutions were disasters, literally. Initial castle designs treated smoke like it would handle itself, which it did by filling every room until people either evacuated or asphyxiated. Central hearths burned in the middle of great halls with no chimneys, just holes in the roof that worked beautifully in theory and catastrophically in practice. Rain poured through the smoke holes. Wind pushed smoke back down into living spaces. Birds built nests in the openings, blocking them entirely. The same defensive features that made castles impregnable also made them uninhabitable. The architectural problem required understanding that wasn't yet available. Medieval builders didn't know about air pressure, convection currents, or thermodynamics. What they had was observation, catastrophic failure, and willingness to experiment on buildings that cost fortunes and represented years of labor. Every burning hall, every suffocated servant, every smoke-logged feast represented data that slowly, painfully taught builders how to make stone fortresses habitable. The genius emerged gradually through hundreds of small innovations that unounded into systems. Individual solutions to specific problems that, when combined, created buildings that could be both defensible and livable. Thick walls that trapped heat could be punctured with carefully positioned openings that created airflow without compromising security. Towers that provided military advantage could also function as chimneys if built with proper internal structure. Stone construction that prevented fire spread could be shaped to channel smoke intentionally rather than randomly. What developed wasn't a single brilliant invention, but an architectural language, a vocabulary of features that addressed multiple problems simultaneously. A tower served defense, but also created height differential that enabled draft. A spiral staircase confounded attackers, but also acted a vertical air channel. Murder holes defended gates, but also vented smoke from below. Every element multitasked, solving the complex equation of making stone fortresses warm, defended, and not actively trying to kill their occupants. The night component was crucial. During daylight, smoke was visible, problems were manageable, evacuation was possible. Night transformed every fire into potential disaster. You couldn't see smoke accumulation. You couldn't easily flee unfamiliar passages in darkness. The fires needed for heating, cooking, and light were most necessary and most dangerous after sunset. Castle design had to prevent panic, had to make nighttime occupation feel safe despite hundreds of open flames burning throughout the structure. This meant creating systems that functioned automatically, that didn't require constant monitoring or intervention. Smoke had to flow out of living spaces naturally. Fresh air had to replace it continuously. Temperature had to remain comfortable without creating dangerous drafts that spread fires. The architecture itself became the safety system. Passive features that worked without human attention, preventing the panic that would arise if people felt trapped in smoke-filled fortresses every night. The sophistication required was extraordinary. These weren't simple buildings. Medieval castles were three-dimensional puzzles where height, thickness, opening position, passage routes, and structural features all interacted to create habitable, defended spaces. Builders developed intuitive understanding of airflow, thermal properties, and smoke behavior through pure observation and iteration. What they created worked so well that the underlying genius became invisible, taken for granted, until you realize what they accomplished without equations or building codes. The fireplace hood represents perhaps the clearest example of architectural problem-solving brilliance. Early medieval halls had central hearths, circular stone areas where fire burned openly. Smoke rose straight up, hit the ceiling, spread outward, and settled throughout the space until breathing became difficult. The ceiling developed black stains, textiles absorbed smell, people coughed through meals. The obvious solution was a hole in the roof directly above the fire, which created new problems involving rain, snow, wind, and seasonal weather, making indoor fires basically impossible. Somebody, probably a desperate lord, tired of freezing and suffocating, commissioned a mason to build a hood. A stone or plaster funnel mounted on the wall above the fire, narrowing toward the ceiling, concentrating smoke and directing it upward through a specific exit rather than letting it disperse randomly. The concept was simple enough that explaining it sounds obvious. The execution required understanding how to support heavy stone structures cantilevered over open flames, how to shape openings for optimal draw, how to position hoods relative to air currents in the room. The first hoods were crude, basically stone funnels that collected some smoke while letting plenty escape around the edges. Masons refined the design through observation and failure. Wider bases captured more smoke. Steeper sides created stronger draft. Rough interior surfaces disrupted airflow and reduced effectiveness. Smooth, gradually narrowing channels worked better. The hood needed to extend far enough from the wall to capture the fire's full smoke output, but not so far that it became structurally unstable or blocked room circulation. The positioning mattered enormously. A hood on an exterior wall could vent directly outside, but exterior walls were often defensive features where puncturing them created security problems. Interior walls required longer flue runs and more complex routing. The height affected draw strength. Too low and the hood obstructed the room. Too high and it didn't capture smoke effectively. Builders developed rules of thumb, proportions that worked, angles that optimized draw without creating structural problems. Materials proved critical. Stone was fireproof, but heavy and required substantial support. Plaster over wood framework was lighter but risky near open flames. Some builders used both. Stone lower down where heat was intense, lighter materials higher up where temperatures dropped. The transition points had to be carefully managed to prevent cracking from differential thermal expansion. Medieval masons understood these issues empirically, building knowledge through observation of what cracked and what didn't. The hood transformed castle halls from smoke-filled caverns into spaces where people could actually breathe while staying warm. This wasn't just comfort improvement, it was survival enhancement. Chronic smoke exposure caused respiratory diseases, eye problems, and reduced life expectancy. Clear air meant healthier populations, which meant more productive workers, more capable soldiers, better defended castles. The architectural innovation had military implications through improved human performance. But hoods created new problems. Smoke concentrated in flues needed somewhere to go, which meant chimneys had to be developed simultaneously. The chimney wasn't a single invention, but a system of related innovations that evolved in parallel with hoods. External chimneys built against castle walls provided the simplest solution, but they were vulnerable to weather, prone to cracking from temperature cycling, and required external scaffolding for construction and maintenance. Internal chimneys, embedded within walls, offered better protection, but required sophisticated planning. The flue had to run through multiple floors without compromising structural integrity or interfering with room layouts. Builders learned to cluster chimneys, running multiple flues through shared stone cores that provided mutual support and conserved building space. Castle architecture began showing characteristic chimney stacks, multiple flues bundled together, each serving different hearths on different levels. The draft physics weren't understood scientifically, but builders figured them out practically. Taller chimneys created stronger draw. Flue cross-section affected airspeed and smoke capacity. Bends and offsets disrupted flow and caused smoke to leak into adjacent spaces. Smooth, consistently sized vertical runs worked best. Builders developed construction techniques ensuring good draft even when theoretical knowledge didn't exist. Build it tall, keep it straight, make it smooth became architectural wisdom encoded in guild practices. Cleaning posed ongoing challenges. Soot accumulated in flues, reducing draw, and eventually blocking passages entirely. The profession of chimney sweep emerged. Young boys sent up flues to scrape accumulated deposits. The work was horrific. Children forced into burning hot passages, breathing soot, risking getting stuck or falling. But it was economically necessary. A blocked chimney meant no fire, which meant no heat, no cooking, uninhabitable spaces. Castle maintenance required regular sweeping, making the abuse of climbing boys structurally embedded in medieval life. Seasonal variations affected chimney performance. Summer heat reduced draft strength, making fires smoke more readily. Winter cold enhanced draw, but also increased the temperature differential between interior and exterior, sometimes causing downdrafts when cold air pushed down unused chimneys. Builders developed dampers, simple metal plates that could close off flues when fires weren't burning, preventing cold air infiltration while maintaining the system when needed. The architectural sophistication extended to positioning hearths and chimneys within room layouts. A fireplace in a corner affected room circulation differently than one centered on a wall. Doors and windows created cross drafts that could enhance or interfere with chimney draw. Builders began thinking systematically about airflow, considering how opening sizes and positions would interact with chimney placement. Castle design became fluid dynamics without the mathematics, pure empirical aerodynamics. Some castles featured multiple hearths in single large halls, each with its own hood and chimney. This distributed heating more evenly, but required careful coordination to prevent one chimney from interfering with others. If chimneys were too close, their exhausts could interact, creating turbulence that reduced draw on all of them. Spacing them adequately while serving rooms efficiently required architectural planning that balanced heating needs, structural requirements, and draft optimization. The hood and chimney system solved the smoke problem, but created heat management challenges. Directing all smoke up a chimney meant directing all heat up there too. Stone and brick absorbed some heat, warming walls and radiating into rooms, but most thermal energy escaped. Castles remained cold despite constant fires, which led to innovations in hearth design, fire backs that reflected heat into rooms, andirons that positioned fuel for better combustion, screens that prevented sparks from escaping while allowing heat radiation. Fuel efficiency became architectural concern. The amount of wood required to heat a poorly designed castle was staggering, sometimes requiring entire forests to supply a single winter's firewood. Better hood design meant more heat stayed in the room rather than escaping immediately. Some builders developed constricted throat designs that reduced the chimney opening while maintaining adequate draft, capturing more heat before smoke exited. These refinements required understanding how airflow, heat transfer, and combustion interacted. The system worked so well that it became standard, spreading across Europe as builders recognized its value and copied successful designs. By the late medieval period, castles without proper fireplaces and chimneys were considered primitive. The architectural sophistication that once seemed advanced became baseline expectation, which is perhaps the highest compliment to effective engineering. Solutions that work become invisible, taken for granted until you realize what they accomplished. Tower design represented another triumph of multi-purpose architectural genius. Towers served obvious military functions, providing height advantage for archers, observation points for spotting enemies, strong points for last-ditch defense. But towers also functioned as sophisticated ventilation systems, creating vertical tear channels that enhanced castle-wide airflow and dramatically improved air quality throughout the structure. The basic physics involved high differentials, creating pressure differentials, creating air movement. Hot air from hearths rose naturally. If you gave it a tall vertical path, that rise in air pulled fresh air in behind it, creating continuous circulation. Towers provided those tall vertical paths, but their military design constraints meant the ventilation function had to be integrated carefully without compromising defense. Spiral staircases within towers served multiple purposes simultaneously. The clockwise rotation, standard in medieval construction, gave defenders fighting downward an advantage, since their sword arms had more room to swing, while attackers climbing had their sword arms against the central column. But those spiral staircases also created continuous vertical passages that air could flow through, functioning as natural ventilation shafts that served every level the tower accessed. Arrow slits and other defensive openings puncturing tower walls created additional airflow paths. These narrow openings were designed to let defenders shoot out while preventing attackers from shooting in effectively. But they also allowed fresh air to enter at multiple heights. The combination of vertical stairwell and multiple small openings created a chimney effect, with air entering through lower slits, warming as it rose through the tower, and exiting through upper openings. The tower breathed, continuously exchanging stale interior air for fresh exterior air. The positioning of tower stairs relative to halls and chambers affected ventilation performance. A stairwell opening directly into a great hall could either enhance or disrupt smoke management, depending on placement relative to hearths and chimneys. Builders learned to position doorways to use natural airflow, placing exits where rising smoke would naturally move toward them, creating intentional draw that pulled smoke away from occupied areas and toward vertical exhaust paths. Some towers featured dedicated ventilation passages separate from staircases, though calling them ventilation passages makes them sound more intentional than they often were. Passages originally built for other purposes, roof access, defensive positions, servant circulation, ended up functioning as air channels. The genius wasn't always in original intent, but in recognizing beneficial side effects and then deliberately incorporating them in later designs. The top of towers presented challenges and opportunities. Crenellations, the tooth-like battlements that defined castle silhouettes, created local turbulence that sometimes disrupted chimney draw from nearby stacks. But they also allowed wind to scour the top of towers, creating low-pressure zones that enhance the draw, pulling air up through the tower structure. Builders learned to position chimney exits relative to crenellations to use this effect rather than fight it. Weather vanes and flags mounted on tower tops weren't purely decorative or informative. Their mounting systems often incorporated openings or caps that both protected chimney exits from rain and enhanced draw through shaped openings that used wind energy to pull air upward even more strongly. The physics weren't understood, but the effects were observed and incorporated. A properly designed chimney cap could dramatically improve draw, reducing smoke problems throughout the connected structure. The thermal mass of thick stone towers provided additional benefit. During the day, stone absorbed heat from sun exposure and internal fires. At night, that stored heat radiated inward, moderating temperature swings and reducing heating needs. This thermal buffering made castle interiors more comfortable while also affecting airflow patterns. Warmer walls created rising air currents along their surfaces, contributing to overall circulation that removed stale air and brought in fresh replacement. Tower clustering in larger castles created opportunities for sophisticated ventilation networks. Multiple towers connected by curtain walls and internal passages formed a distributed system where air could flow through multiple paths. The system became self-regulating to some extent, with air taking paths of least resistance, automatically adjusting to wind conditions, fire activity, and seasonal temperature variations. The architecture created adaptive ventilation that worked without human intervention. The strategic placement of passages connecting different areas allowed intentional routing of airflow. A passage from kitchen to great hall didn't just allow servant movement and food delivery. It created an air path where smoke and heat from cooking could be drawn toward the hall's fireplace and chimney system rather than accumulating in kitchen spaces. Doorways became part of the ventilation design, with size and positioning chosen to facilitate desired air movement patterns. Some towers included garderobe chutes, basically built-in latrines where waste fell through vertical shafts into moats or pits below. These shafts, though intended for waste disposal, also functioned as ventilation paths, though probably not in desirable ways. The principle of using vertical passages for air movement was understood, even if the specific applications were sometimes unfortunate. Every penetration of the castle's mass created potential airflow, and builders learned to use these paths intentionally. The height of towers varied based on military needs, but taller towers provided better ventilation alongside better observation. A tower rising 50 feet created significantly stronger draft than one rising 30 feet. Lords wanting better ventilation had to invest in taller towers, which meant more expensive construction, longer build times, more material, but also superior defensive capabilities. The costs were justified by military benefits, even if ventilation improvement was considered a pleasant side effect. Regional variations in tower design reflected different climate challenges and architectural traditions. Northern European castles with more severe cold emphasized heat retention, using smaller openings and thicker walls, accepting reduced ventilation to keep more warmth inside. Mediterranean castles in warmer climates used larger openings and more generous ventilation, prioritizing air circulation over heat retention. The same architectural elements adapted to different environmental demands, showing the flexibility of the underlying principles. As artillery developed and military architecture evolved, the purely military function of towers diminished, but their residential value increased. By the late medieval period, towers were being built primarily as prestigious residential quarters with better views, more privacy, and superior air quality compared to lower castle areas. The architectural elements that once served defense now served comfort, demonstrating how features could outlive their original purposes when they solved multiple problems effectively. The window represents another element of genius, multifunctionality. Obviously, windows provide light, but their role in managing smoke and wind was equally critical and much more carefully considered than most people realize. A window isn't just a hole in a wall. It's an interface between interior and exterior environments, a control point for airflow, light, temperature, and security, all simultaneously require an architectural balance. Early medieval castle windows were minimal, basically narrow slits that provided defensive positions while letting in small amounts of light. These arrow loops were terrible for ventilation because they were small and positioned for military rather than environmental purposes. As castle living evolved from purely military to residential, window design had to expand to provide better habitability while maintaining defensive strength. The development of larger windows required solving several problems simultaneously. Structurally, large openings in thick stone walls need proper arches or lintels to carry the weight above. Militarily, larger openings create vulnerabilities that enemies could exploit. Environmentally, bigger windows mean more heat loss in winter, more unwanted air intrusion during storms, more exposure to weather generally. The solution wasn't making windows simply larger, but making them selectively permeable, controllable interfaces. Shutters became critical components, converting windows from permanent openings to adjustable ones. Wooden shutters could seal windows against weather and attack, while allowing them to be opened for ventilation and light when appropriate. The shutter mechanism required careful design, since poorly fitted shutters leaked air and water while adding minimal protection. Well-made shutters that sealed properly when closed transformed windows into sophisticated control elements. The positioning of windows relative to prevailing winds and sun angles affected their performance dramatically. Windows on windward walls created positive pressure, forcing air into the building. Windows on leeward walls experienced negative pressure, pulling air out. By opening windows strategically on opposite walls, builders could create cross-ventilation that rapidly exchanged interior air. This required understanding local wind patterns and positioning windows to take advantage of them. Height placement mattered enormously. Lower windows brought in cooler air that would then be warmed and rise. Upper windows, especially those in towers, provided exits for warm, stale, smoke-contaminated air. The combination created thermal siphoning, where heat itself drove air circulation. A great hall with low windows on one wall and high windows or openings on the opposite could create strong natural circulation powered by fire heat. Window size variation throughout a castle reflected different functional needs. Small windows in storage areas where security and temperature stability mattered, Larger windows in living quarters where light and air circulation took priority. Minimal windows in defensive positions where vulnerability had to be minimized. The variation created a hierarchy of environmental control matching the hierarchy of space usage. Glass changed window functionality dramatically when it became affordable. Glazed windows could admit light while blocking wind and rain, allowing windows to function even in adverse weather. Early glass was expensive and often of poor quality, wavy and distorted, but it sealed openings while maintaining transparency. The combination of glass panes and movable shutters created maximum flexibility. Light without drafts when desired, full sealing when necessary. The development of hinged casement windows added another level of control. Instead of just blocking or unblocking an opening, casement windows could be partially opened to precise angles, fine-tuning airflow to match current needs. A window opened fully created maximum ventilation. Open slightly created gentle air exchange. The angle could be adjusted in response to wind strength, temperature, smoke levels, creating adaptive environmental control. Some windows incorporated fixed upper sections with operable lower sections, providing permanent light admission with adjustable ventilation. Others used opposite configurations with operable upper sections that could vent rising heat without creating uncomfortable drafts at floor level. The specific configuration matched room use and environmental priorities, showing sophisticated understanding of how different design choices created different environmental effects. Seasonal usage patterns developed around window management. Summer meant maximum opening to promote air circulation and cooling. Winter meant keeping windows closed, except when smoke accumulation required ventilation. Spring and fall required balancing between thermal comfort and air quality. Castle occupants learned to read environmental conditions and adjust windows accordingly, using architecture as interface between interior and exterior environments. The labor required for window management was significant in large castles. Opening and closing dozens of shutters throughout a structure required servants who understood which windows to adjust when, creating optimal conditions while avoiding problems like rain entering open windows during storms. This operational knowledge became part of castle household management, passed between generations of staff who understood the specific behavior of their particular building. Security requirements meant windows on lower levels remained small and well defended, even as upper-level windows grew larger and more generous. This created interesting architectural effects where castle elevations showed clear vertical gradients, progressing from minimal lower openings to more generous upper ones. The gradient reflected the balance between defensive necessity and environmental benefit, showing how both requirements shaped architectural form. The relationship between windows and chimneys required careful coordination. If windows weren't properly positioned relative to fireplace chimneys, opening them could create backdrafts that pushed smoke into rooms rather than clearing it. Builders learned that windows should be positioned to work with chimney draw, not against it, creating airflow patterns that supported rather than disrupted smoke management. This required thinking about the entire environmental system rather than treating elements in isolation. Night posed special challenges for window management. Closed shutters sealed openings but trapped smoke and stale air. Open windows provided ventilation, but created security vulnerabilities and allowed temperature to drop uncomfortably. The solution often involved partially opening upper windows that provided smoke ventilation while being difficult to access from outside, maintaining basic security while preventing air quality problems that would cause panic or evacuation. The murder hole, though designed for deadly defensive purposes, functioned brilliantly as ventilation feature. These openings in ceilings or floors above gates and passages allowed defenders to drop projectiles, burning oil, or other unpleasant surprises on attackers. But they also created vertical air paths connecting different levels, enhancing circulation throughout gate passages and adjacent spaces. The typical murder hole, positioned above a gate passage, faced an interesting environmental problem. Gate passages were enclosed areas where smoke from torches and fires used to defend the gate could accumulate dangerously. Guards stationed there needed to breathe while also needing to protect the entrance. The murder hole, by creating an opening to spaces above, allowed smoke to rise out of the passage, keeping it relatively clear even during defensive operations. The size of murder holes reflected this dual purpose. Too small and defensive effectiveness dropped. Too large and security was compromised. The size that provided adequate defensive capability happened to also create reasonable ventilation, showing how practical constraints often led to solutions that balanced multiple requirements effectively. A hole large enough to drop a rock through was large enough to let smoke escape effectively. The positioning of murder holes in vaulted ceilings created interesting fluid dynamics. Vaulted architecture naturally directed rising air toward the apex of arches. Murder holes positioned at these high points captured air that was already moving upward, maximizing ventilation effectiveness. The defensive and architectural elements reinforced each other, creating systems greater than the sum of individual features. Multiple murder holes in a single passage created redundancy. If one became blocked by debris, others continued functioning. For ventilation, this meant distributed exhaust points that cleared smoke more effectively than a single opening could. The passage remained breathable, even if smoke production exceeded the capacity of any single exhaust point, providing safety margin against environmental disaster. Connecting passages above murder holes extended the ventilation path. Smoke exiting through a murder hole entered an upper chamber or passage that itself vented to exterior through windows or other openings. This created two-stage exhaust that prevented smoke from simply accumulating in the upper space, ensuring actual removal from the building rather than just relocation to a different area. This just feels safe and comforting. The thermal effects of murder holes contributed to their ventilation performance. Gate passages were often among the coldest parts of castles since they connected interior to exterior directly. Any heat generated there from torches, fires, or human bodies created strong buoyancy that drove air upward through murder holes effectively. The combination of thermal and architectural design created robust ventilation even in challenging environments. Maintenance of murder holes presented challenges since they were often positioned in inaccessible locations high above passages. Soot accumulation could reduce effective opening size over time. Debris could block them entirely. Yet their defensive importance meant they received attention, and cleaning them for military readiness also maintained their ventilation function. The dual purpose ensured they remained operational even when pure environmental benefits might not have justified the effort. Some castle designs incorporated decorative grating over murder holes, partly for aesthetic reasons, but also to prevent large objects from falling through accidentally while still allowing airflow and intentional defensive use. These gratings showed architectural refinement, taking a purely functional feature and elevating it to something that contributed to interior appearance while maintaining performance. The psychological effect of murder holes operated alongside their physical functions. Knowing that smoke had escape paths prevented the panic that would arise from feeling trapped in smoke-filled enclosed spaces. Guards could perform their duties confident that breathing wouldn't become life-threatening even during extended defensive operations. The architectural feature provided psychological safety alongside physical safety. Regional variations in murder hole design reflected different defensive priorities and architectural traditions. Byzantine castles featured elaborate machicolations with multiple openings. Western European keeps used simpler single openings. Islamic fortifications sometimes incorporated them into decorative patterns that disguised defensive purpose. Each tradition arrived at similar solutions through different design languages, showing how functional requirements drove convergent architectural evolution. The integration of all these elements created environmental systems of remarkable sophistication. A castle wasn't just a collection of defensive features or residential rooms. It was an integrated environmental machine where air entered through windows and arrow slits, circulated through halls and passages driven by thermal effects from fires, smoke concentrated in hoods and chimneys, exhaust paths led upward through towers and murder holes, and fresh air continuously replaced contaminated air in a cycle that required minimal human intervention. The system worked passively, powered by temperature differentials, wind, and natural buoyancy. No pumps, no fans, no active controls beyond opening and closing shutters and managing fires. The architecture itself created environmental management, showing extraordinary understanding of how buildings interact with natural forces. Medieval builders had no equations or scientific theory, but they had observation, iteration, and accumulated wisdom encoded in architectural practices. The night component became critical because fires burning throughout the structure created maximum smoke load exactly when darkness made problems most dangerous. The architectural systems had to handle peak demand during conditions when evacuation would cause panic and injury. Windows could remain partially open overnight in secured upper levels. Chimneys continued drawing steadily. Towers maintained circulation. Murder holes vented passage smoke continuously. The system operated automatically, requiring no nighttime intervention to prevent disaster. This automation prevented panic because occupants could trust that breathing would remain possible throughout the night without constant vigilance or emergency evacuation. People could sleep secure in knowledge that architectural systems managed environmental challenges. The alternative, buildings where smoke accumulation required periodic evacuation, or where breathing became difficult during normal occupation, would have created constant anxiety and made castle living intolerable. The robustness of these systems showed in their tolerance for partial failure. If one chimney drew poorly, others compensated. If windows needed to close due to storms, tower ventilation continued. If smoke production exceeded normal levels due to additional fires or events, the system handled peaks with grace degradation rather than catastrophic failure. This resilience came from redundancy and capacity margins built into architecture through empirical understanding of worst-case requirements. The efficiency improved over centuries as builders learned from experience and shared knowledge. Early castles suffered frequent smoke problems, discomfort, and occasionally fatalities from poor air quality. Later castles, incorporating generations of accumulated wisdom, operated much more reliably, providing comfortable habitation that supported long-term occupation without health effects or operational problems. The learning curve was painful but effective. Economic factors drove improvements since uncomfortable castles reduced military readiness and productivity. Soldiers who couldn't breathe properly couldn't fight effectively. Workers suffering from chronic smoke exposure performed poorly and died young. Lords who prioritized habitability alongside defense gained advantages in attracting and retaining quality personnel, creating competitive pressure that rewarded architectural innovation. The spread of architectural knowledge happened through multiple mechanisms. Master masons moved between projects, carrying techniques with them. Nobles visiting other castles observed successful features and requested similar implementations. Military engineers studying fortifications noted which designs supported better garrison health and morale. The knowledge accumulated and dispersed across Europe, leading to progressive improvement in castle environmental performance. Some innovations remained regional, reflecting local conditions that shaped priorities. Alpine castles emphasized snow load management and extreme cold protection. Mediterranean castles focused on heat rejection and sun shading. Coastal castles dealt with salt air and humidity. Each region developed architectural responses to its specific challenges while sharing universal solutions to common problems like smoke management and ventilation. The transition from purely military fortifications to residential castles accelerated environmental innovation. When lords began living in castles year-round rather than using them only during conflicts, habitability became priority alongside defense. This drove refinements like better windows, improved fireplaces, sophisticated ventilation, and attention to comfort that military-only structures didn't warrant. The architectural evolution reflected change in usage patterns. By late medieval period, castle design had reached remarkable sophistication in environmental management. The best examples provided comfortable, healthy, secure habitation that balanced military requirements with human needs effectively. The architectural achievements represented centuries of empirical learning, codified into building practices that produced consistently good results even without theoretical understanding of underlying physics. Modern appreciation for these achievements often misses how extraordinary the engineering was. We take for granted that buildings provide shelter from weather while admitting light and air. We assume ventilation removes smoke and provides fresh air. We expect architecture to protect us from environmental extremes while maintaining habitable conditions. Medieval builders created all this without benefit of science, building codes, or modern materials, using only observation, experience, and accumulated craft knowledge. The comparison to modern buildings reveals both similarities and differences. Contemporary HVAC systems use mechanical equipment to force air circulation, but the principles remain similar to castle ventilation. We still use vertical shafts to exhaust contaminated air. We still position openings to utilize natural air pressure differentials. We still use building mass for thermal buffering. The specific implementation changed, but the underlying strategies medieval builders developed remain valid. Some argue that medieval castle environmental management was more sustainable than modern approaches, since it required no external energy, operated purely on natural forces, and maintained comfort using passive architecture rather than mechanical systems. Whether this nostalgia is warranted is debatable, but it highlights how effective the medieval solutions were, given their constraints. They created habitability without consuming resources beyond construction materials and firewood. The lessons from modern architecture include the value of passive environmental control, the importance of integrating multiple functions into single features, and the effectiveness of observation-based design refinement. Medieval builders proved that sophisticated environmental management doesn't require advanced technology if you understand natural forces and design architecture to work with them rather than against them. The principles remain applicable even as implementation tools advance. The human stories behind these architectural achievements deserve recognition. Anonymous masons who observed smoke patterns and adjusted chimney designs. Lords who invested in better ventilation despite higher costs. Residents who suffered through poorly designed earlier castles and pushed for improvements. Guards who froze in drafty towers or suffocated in smoke-filled passages until design evolved to address their needs. Every architectural feature represents human experience, often painful, that drove innovation. The craftsmen who actually built these features possessed remarkable skill. Creating tall chimneys that remained stable and weathertight required precision stonework. Installing window frames in thick walls demanded careful planning and execution. Building spiral staircases that served multiple purposes simultaneously required three-dimensional thinking and exact calculation using only geometry and experience. The craft mastery underlying castle architecture was profound. The testing and refinement happened in real time with occupied buildings. You couldn't prototype a castle and iterate designs quickly. Each construction represented massive investment that had to work reasonably well immediately, and then be refined gradually through modifications and repairs. The development process was slower than modern engineering, but still effective, producing progressive improvement across generations of construction. Thank you for spending these hours exploring castle environmental engineering with me. If you found value in understanding how medieval builders created sophisticated ventilation systems without causing nighttime panic, I'd appreciate if you'd subscribe to Candle History and share your thoughts. What surprised you most about castle design? What modern parallels do you see in how we solve architectural problems? I read every comment and value the discussion. We began with buildings designed to kill you that learned not to. Now, hours later, you understand that medieval castle design represented some of history's most sophisticated environmental engineering, creating passive systems that managed smoke, wind, heat, and human survival through pure architectural cleverness. The genius wasn't in any single invention, but in the integration of multiple features into coherent systems that solved complex problems without requiring constant intervention. The modern world has largely forgotten these achievements because they worked too well. Successful passive architecture becomes invisible, taken for granted, until you realize that making hundreds of people survive comfortably in stone fortresses heated by open fires without suffocating them or burning the building down required extraordinary ingenuity. Medieval builders accomplished this through observation, iteration, and accumulated knowledge that they encoded into architectural practices still influencing building design today. The panic prevention component reveals understanding of human psychology alongside physical engineering. Creating systems that functioned automatically at night when darkness magnified every environmental problem showed that builders grasped both technical and psychological requirements for habitability. Architecture had to not just work, but create confidence that it would continue working even when you couldn't see or directly control conditions. The integration of military and residential requirements produced architectural sophistication that purely residential buildings didn't achieve until much later. When every feature has to serve multiple purposes, when stone walls must simultaneously defend against armies and retain heat, when towers must provide military advantage while improving ventilation, you develop design thinking that considers complex interdependencies rather than optimizing individual functions in isolation. The empirical engineering approach medieval builders used proved remarkably effective, despite lacking scientific theory. They couldn't calculate airflow or thermal transfer, but they could observe what worked and codify successful practices into repeatable methods. This craft-based empirical approach produced results comparable to what modern engineering achieves through calculation, demonstrating that accurate observation and careful iteration can substitute for theoretical understanding when necessary. The sustainability lessons remain relevant. Creating habitable buildings using only passive systems powered by natural forces shows possibilities for modern architecture trying to reduce energy consumption. While we probably don't want to abandon mechanical environmental control entirely, incorporating more passive strategies inspired by medieval solutions could reduce resource use while maintaining comfort. The old knowledge has modern applications if we're willing to learn from it. The regional variations in castle design reflect the eternal truth that architecture must respond to local conditions, that universal solutions rarely work as well as adapted ones, that builders must understand their specific environmental challenges and create responses suited to them. Climate, materials, military threats, economic resources all shaped castle architecture differently in different regions, while maintaining common threads of functionality. The social dimensions of castle environmental engineering show how architecture affects human welfare directly. Better air quality meant healthier populations, which meant stronger military forces, which meant more secure territories, which created conditions for economic development and cultural achievement. The chain of effects demonstrates how solving immediate practical problems through good design creates broader benefits that justify investment in quality architecture. The craft transmission mechanisms that spread castle design improvements across Europe foreshadowed modern knowledge-sharing networks. Master masons traveling between projects, nobles commissioning features they'd seen elsewhere, military engineers studying enemy fortifications and adopting useful elements, all created distributed innovation networks that progressively improved architectural performance. The mechanisms were slower than internet speed information sharing, but still effective. The accumulated cost of developing these systems through centuries of experimentation was enormous. Every failed chimney design, every smoke-logged hall, every suffocated resident represented expense in construction, health, and human life that contributed to eventual understanding of what worked. We inherit the benefits of that costly learning without bearing the costs, making it easy to underestimate the achievement. The timeline required shows patience and long-term thinking that modern development often lacks. Architectural improvements weren't implemented immediately across all castles, but spread gradually as new construction incorporated lessons learned, and existing buildings underwent modifications. The process took centuries, but it produced robust solutions that worked reliably once perfected. What's remarkable is how well the systems actually worked once refined. Late medieval castles provided genuinely comfortable habitation with good air quality, adequate warmth, and minimal smoke problems. The architecture successfully solved challenges that had plagued earlier buildings, creating environments where people could live healthy, productive lives despite the constraints of stone construction and open fire heating. That success justified the development investment. The preservation of these architectural achievements in surviving castles allows modern study and appreciation. We can visit medieval castles, examine fireplaces and chimneys, trace ventilation paths through towers, understand murder hole placement, and see firsthand how the systems were implemented. This physical evidence, combined with historical records, provides a complete picture of how the engineering actually worked. The influence on subsequent architecture extended far beyond castles. The fireplace and chimney systems developed for castles spread to manor houses, town buildings, and eventually modest dwellings as the technology became more affordable. The environmental engineering innovations that made castles habitable eventually improved housing quality broadly across society, showing how solutions developed for elite structures trickle down to general benefit. The military obsolescence of castles as artillery advanced didn't immediately reduce their residential value. Many castles continued occupation long after they ceased being militarily relevant, because the environmental systems made them comfortable homes. The architecture outlived its original purpose, demonstrating how well-designed buildings adapt to changing uses when underlying environmental engineering remains sound. Today's castle ruins offer silent testimony to architectural genius that solved problems most visitors never recognize existed. The chimney stack that seems like simple decoration was carefully positioned to catch wind and enhance draw. The tower that looks purely military created airflow that refreshed entire sections of building. The window that appears randomly placed was positioned to work with prevailing winds and sun angles. Every feature repays careful study. The preservation challenges facing castle ruins include environmental systems decay, chimneys collapse, roofs that once protected ventilation paths disappear, windows lose shutters that controlled their function. What remains shows architectural form, but not complete function, making it harder to understand the sophisticated environmental engineering that made the structures work. Preservation should include not just static conservation, but documentation of how systems operated. The educational value of understanding castle environmental engineering extends beyond architectural history. It demonstrates principles of passive design, multifunctional features, observation-based engineering, craft knowledge development, and human-centered problem-solving that remain relevant today. Castle architecture was engineering in service of human needs, creating built environments that supported life effectively despite severe constraints. The craftsmen who created these solutions deserve recognition as engineers, even though they lacked formal engineering credentials. Their empirical approach produced results that theoretical science later explained and refined.